Okay, so what do we always do next? We take something like this and we multiply it out so that we can relate different quadrants of the result to, in this case, the original matrix A. So we take this, but what do we know? We know how to multiply two partition matrices together. You've done this a lot of times by now. So this is just this times that plus 0 times that. So the top left quadrant is L top left times U top left. This quadrant is this times that plus this times 0. So that's L bottom left times U top, L bottom left times U top, L bottom left times U top left. And then this quadrant here is this quadrant here is this times that plus this times that. That's L top left times U top right. And finally, this bottom quadrant here is a little bit more complicated. It's this times that plus this times that. Which then must be equal to the different quadrants of the original matrix. And now what we have is we know that the top left of L times the top left of U must be equal to the top left of A, the original contents of that, etc. Okay? And that means that we now have a partitioned matrix expression. Okay, now let me take a minute and write that down a little bit cleaner. Okay, so now the question becomes, how do we take this partitioned matrix expression and how do we extract different invariants out of this? And this gets a little bit tricky because you can't go and say, let's only compute L bottom right and U bottom right. Because inherently, if you look at it, in order to compute L bottom right and U bottom right, you would have to use the fact that this plus that is equal to that. So you would somehow have to update this with this. But if you haven't computed that yet, then you can't do that. So the point I'm trying to make is that there is an inherent order in which some of these things must be resolved. Okay?